In this video, we're going to cover 6.6, and that's on the law of cosines. So in the last video, which was on 6.5, we looked at the problem of so-called solving a triangle, which meant you're given a certain amount of information about the triangle, lengths of sides maybe, or angle measures, and then you wanted to determine the rest of the information, the relevant or pertinent information about a triangle from the given data. And we saw that there were the four cases, and the first two of which could be solved using what we called the law of sines, which were a set of equations that related angle measures and side lengths. There was these ratios. So the law of sines could be used to solve triangles where you knew two sides and an angle between them, or if all three sides were known. So that's kind of what those, that's the sort of cases that fell under the law of sines. It was applicable to those cases. I'm sorry, no, that's what the law of cosines will be able to handle. So I'm sorry, I got that backwards. The law of sines, let me just bring it up. The law of sines could handle the first two cases, which were you had one side and two angles. So that was the angle side angle and the side angle angle case. And then there was two sides and an opposite angle opposite those sides, or one of those sides could be used. So let me share my screen and open it up. Open up the book. So we had these two cases are here were fell under the umbrella of the law of sines. That is to say, they were applicable. The set of equations were applicable to these two cases. So that's, for example, the two sides and an angle opposite the one of the sides. That's side angle. So you're given this side, and then this angle, which is opposite to this side right here. You're given that angle, and you want to determine the rest of the relevant information about the triangle. And you could use the law of sines to do that. But we had these two other cases, 3 and 4, where two sides and an included angle, or all three sides are known, that you could not apply the law of sines to that. So here are examples of the last two cases. So side, angle, side. You're given two sides and an included angle. I guess that's the term they use. Yeah. So this angle that's kind of defined by those two sides, because remember, the angle is, two rays which share an origin, or vertex maybe, or origin. I suppose you could use either term. So here's the vertex that this ray and this ray share, and there's the angle defined by those two rays. And then the other case that law of cosines can handle is the side case. And that's what we're going to deal with in this video section. We're going to talk about section 6.6, which is on the law of cosines. And I just realized I don't have my tablet plugged in. Okay, so we have 6.6. This is law of cosines. So the book has a proof of the law of cosines, but I'm not going to go through it. Although I encourage you to look at it. The proof is pretty straightforward, and there's a picture sort of illustrating the proof of why these formulas hold. So I'm just going to write down the formulas. So we have, the setup is we have some triangle ABC, just any triangle. It doesn't have to be a right triangle. We have angle A, angle C, and angle B. And we have to be careful about our triangle convention. We have to be careful about how we're labeling it. Otherwise, the equations might not hold. So we have angle A, C, B. We put them in this way. I mean, you can do A, B, C, but you just got to be careful about how you label the sides. So if you label, however you label the angles will determine how you're going to label the sides. So what you need, though, on however you label it, is you need the side opposite the angle to have the same letter. So here's angle A, there's side A right here, or side whose length is A. Here's angle B, and then here's the side which it is opposite to, and that has a length of B. So you just got to be careful about how you label the triangle. You can label the angles however you want, but you just got to make sure that the sides correspond to that labeling, the way you label the sides. So the law of cosines is that in any triangle ABC, we have the following system of equations. And these should kind of remind you of the Pythagorean theorem. In fact, that's sort of how you prove the Pythagorean theorem. But the idea is, like, you start with an arbitrary triangle, and then you you start with an arbitrary triangle, and then you sort of make it into a right triangle, which can then, from which you can then use Pythagorean theorem and the distance formula. I guess that's really what they're using, the distance formula, but the distance formula is kind of the Pythagorean theorem. So maybe I will just pull it up because it's kind of neat, the proof. The idea is, the proof is, you just start with some triangle right here. See, just arbitrary triangle, not necessarily a right triangle. But then you take this side, or I guess it doesn't really matter which side you take, and you drop down this line to get a right triangle. And you can get these coordinates based on the coordinates of the other points. And then, as it says, you just apply the distance formula. So you're looking at, yeah, you just get the coordinates of the vertices. So if you know, yeah, so yeah, if you just know these things, and you can basically, in some sense, make a right triangle from the given triangle, then you can use the distance formula and you'll prove the result. You just got to do some of this algebra here. So it's not that bad. I would definitely read this. This is pretty illustrative of what a decent proof is. This is actually a pretty rigorous proof right here, which is not something you really see in pre-calc books, like a rigorous proof, actually. So I encourage you to look at that. So the point, though, that I want to make is that these should look like the Pythagorean theorem, but you have like this term, which I'll point out, that you have to like almost correct it by. So we have a squared is equal to b squared plus c squared. So this is the Pythagorean theorem right here. But because we're not necessarily, because ABC is not necessarily a right triangle, you have to subtract off this piece to correct for the fact that it's not a right triangle. Now, no, if like, yeah, you got to subtract off this term right here. So this is Pythagorean theorem right here. And then this is like this term you have to subtract off, because you have to like correct for the fact that this triangle you start with might not necessarily be a right triangle. But notice, if A is a 90-degree angle, so in other words, you are dealing with a right triangle, this is 0. So if A is equal to 90 degrees, or pi over 2 radians, cosine of A is equal to 0. I don't like how I wrote this. And so you get the Pythagorean theorem. So the Pythagorean theorem actually follows from the law of cosine. So let me just write this again a little more neatly. So if A is a 90-degree angle, or equivalently pi over 2 radians, then cosine of A is equal to 0. So this whole term, it goes to 0, and you just have a squared equals b squared plus c squared, which is the Pythagorean theorem. The formula we're all hopefully familiar with at this point. So yeah, if your A is a 90-degree angle, in other words, if you're dealing with a right triangle, you get you actually get the Pythagorean theorem. You don't have to worry about this correction term here. You don't have to subtract anything off because that term is just 0. So this is the first equation. There's some other equations. They're similar. And notice when I write these down, we'll look at how to sort of memorize these formulas. So you have b squared equals a squared plus c squared minus 2ac cosine b. And then you have c squared is equal to a squared plus b squared minus 2ab cosine c. So all these two formulas right here, they're kind of just like you would say is they're a permutation of this above equation. They're like you just like swapping the letters around. So you're like permuting the letters in some sense. So what's going on here is that you have on the left hand side you have just this lone term a squared. And so you have these three sides. You have the lone term on the one side, and then the remaining two sides on the other side of the equation. So, and then the angle that's in the equation is the angle whose name corresponds to that side length. So see, there's this correspondence here. The A goes here, so this A goes here, and then you just put the remaining sides here, and you take their product over here. So, and then the same thing down here. You have b squared is equal to a squared plus c squared minus 2ac cosine b. So you have the b term on the left-hand side, so that's the length of the one side. So you have to put that b angle over on this side, and then you need the remaining lengths, so you put them on the other side of the equation, and their product is over here. So, and the same thing with this equation. So hopefully what I'm trying to say makes sense. It's just like a way of memorizing these equations. Like, where do the letters go? So let's look at an example. All right, let's look at two examples. So this video should be relatively short. Fingers crossed. So this is example 2 in section 6.6. So this is an example of side, side, side. How do we deal with that? How do we use the law of cosines to deal with that sort of triangle? So the setup is the following. We have this triangle. We don't know any of the angles, so we'll just label them this way. That's the information we want to determine. But what we are given is the length of all the sides. So we're going to label these, and we're given the sides but not the angles. So we want to determine the angles. So first of all, let's look at, I'm not going to go through each one of them because they're all basically the same. So let's find angle A. Well, remember, so the equations have cosine of some angle on the right-hand side, cosine of some angle. So we want the one that has cosine of A in it. So if you have cosine A in the equation, on the right-hand side in particular, then the thing on the left-hand side is going to be the a squared, right? That's how you kind of remember these equations. So the equation we want is a squared is equal to b squared plus c squared minus 2bc. So that's the correspondence here between The product that you take is just the product of those sides that appear on the right-hand side. And then this is 2bc times cosine of A. So this is what we want to solve for. So if you do that, you can put a squared and c squared on both sides. So you, on the left-hand side, you'll have a squared minus b squared minus c squared minus 2bc cosine A. And then I will divide both sides. I'm going to flip the equation, so I have cosine on the left-hand side. But what I'm going to do is divide both sides by 2bc, and that will isolate cosine A. So yeah, let me just do that, and then I'll do simplify once more. So I divided by minus 2bc. And then if I can cancel this negative and flip the terms around a little bit. So, well, first of all, I should point out I can divide by 2bc because we're talking about lengths of a triangle. We're never going to deal with what's a so-called degenerate triangle. In other words, a triangle with lengths, side lengths of 0. Such, you can consider that as a triangle in a strict sense, but it's not a very interesting triangle. So we can divide by 2bc. We're not dividing by 0 in any case because we're all A, B, and C are always going to be positive numbers. In particular, they're not going to be non-zero. But if I cancel this negative with the negatives in here, I had to throw a negative on the A, right? And then I'll just rearrange it to get this. So make sure you understand what's going on here, this algebra right here. Why can I go from here to here? How am I canceling these negatives? Make sure you understand all of these steps. So now I'm going to plug in some numbers. So we know B, C, and A. We know all of these numbers. So now we can plug in. And this is a good thing too, especially when you go to physics. You're going to give, like if you're doing lab work. I remember having to do all this that nonsense because I was a physics major. I was actually going to go to PhD in physics, but then I went into math. So I just felt like the mathematicians understood theoretical physics better than the physicists. But anyways, that's just an opinion. If you go into physics or you take a physics class, even just one, you're going to have to deal with equations and really awful numbers, way more awful than we've been dealing with. Lots of decimals and just horrible. So one thing that they will tell you is never plug in numbers at the beginning. Always do the algebra first and then plug in the numbers. That's precisely what we did here, because then you're going to have to kind of carry down these awful, hideous numbers throughout these calculations, and you don't want to do that. So get in the habit of doing your algebra first and then plugging in the numbers, because it's a lot cleaner. You'll probably lose points if you do that. You probably lose points if you don't do that. That is, do the algebra first. So let's plug in some numbers in. So B was 8, so we had 8 squared. C was 12, so 12 squared. And then A is 5, so 5 squared. And then in the denominator, we have 2 times 8 times 12. And if you do the if you simplify this, you'll get 183 over 192. And if you're interested, I mean, I don't really care what the book gives it, so I'll give it. If you're interested, this is approximately 0.953125 for what it's worth. Oh, actually, no, it's exactly equal. What am I talking about? This is a rational number, so it has a finite. Rational numbers have finite decimal expansions. So this actually just equals that. But again, I don't really care. So I don't really expect you to care either, but I'll write it down because the book writes it down. So if you do that, now we have cosine A is equal to this number. So we can solve for it. We can say A is equal to cosine inverse of 0.953125. And to get that, you're going to have to use a calculator. In this case, you will get an approximation. This won't be actually equal to it. It's probably an irrational number, so it won't have. This is probably irrational, but maybe, I don't know. Don't take my word for it. More than likely it is. So this will be approximately 18 degrees, and you can get some radian numbers if you want. Not expected. And then you basically just go through the same exact procedure to find angle B and then angle C. You use the appropriate equation. You look for the equation that has, so for example, if we're going to solve for cosine B, look for the appropriate equation, the equation that has cosine B in it. Solve for cosine B, then plug in all your numbers and take the inverse cosine of both sides. Use a calculator if you have to. I should be assigning problems where you don't. It's not necessary to use a calculator. I think there are problems that don't require a calculator. If there are, I will choose those. But then at that point, you can plug in a calculator if you want to. But even this is enough right here for me. Or actually even better, because I don't want to have to think about all these decimals, just cosine inverse of 183 over 192. That's better for me. We're not physicists, so we don't deal with awful numbers. So yeah, that's solving for angle B and C is basically the same. So I'm not going to go through that. So that was an example of side, side, side. Now we're going to go through example 3, and this is an example of side, angle, side. So example 3, side, angle, side. So this is the other sub case. We have those. Remember, we had those 4 cases, and this is the other case that it can deal with. You can use the law of cosines to solve. So the setup is the following. We have this triangle, and we're not given A. We're given C, though, the angle measure of C, and that we're told that it's 92.8 degrees. We're given side B, which is 10.5. We're given side A, which is, for some reason, approximately 13. Oh, no. That's what we're going to solve for, I think. I mean, it doesn't matter if you saw it. Yeah, we don't know what A is. But we do know what C is. We're told it's 18.0. And we don't know angles A and B. So we need to solve. We need to find A, side A, and angles A and B. So we can, all of the formula, so let's look for side A first. So all the formulas involve side A, right? But there's one in particular that's very easy to solve for. In fact, it's basically, you don't even have to do hardly any algebra. It's already in the form where you can solve it. And that's the one where you have A squared on the left-hand side and the other terms on the other side, the other lengths of the sides. And so if A is on this side, that means B has to be on the right side, squared, and C squared has to be on the other side. And then if B and C are on the right side, that means their product is also on here, B and C. So 2 times BC cosine A. So we can plug some numbers in now. Oops. And we'll get A squared is equal to 10.2 squared plus 18.0 squared minus 2 times 10.5 and then 18.0 cosine of 46. Wait, hold on. Something's not right. Oh, I'm sorry. Angle C is not given. I made a mistake here. That's something we want to find also. What we are given is angle A, and that is 46.5 degrees. So 46.5 degrees. If you plug this into the calculator, you'll get that this is approximately 174.05. And then you take the square root of both sides. You ignore the negative root, right? Because lengths have to be positive. So A is going to be approximately square root of this, which is, if you plug into your calculator, approximately 13.2. Now I won't go through, so we found the missing side. Now we just need the two angles, which are C and B. I'll just go through solving B because solving C is basically the same thing, and it's actually similar to what we did above. But I'll just do it I'll do it one more time because this is the last example. So, well, yeah. So let's just look back at the equation, the law of sines. Oh, I think I went too far. Okay, this one right here. So we want to solve for cosine B, so we can get angle B. Well, it's going to involve the same sort of algebra we saw in example 2. I subtract a squared and c squared from both sides, and then if I divide by negative 2ac, and then those negatives cancel out nicely. And if you do that, what you'll get is that cosine B is equal to a squared plus c squared minus b squared. So make sure you understand how I got this right here. How did I get that cosine B is equal to this? Go through the algebra yourself. I already went through the algebra once, so I'm not going to go through it. Or I went through similar algebra when I solved for cosine A. I'm not going to go through it again, so I'll let you do that. And of course, if you run into troubles, you can't figure it out, just email me, or so we can work it out over the email, or we can meet via Zoom. So if you plug in, we know A, B, and C. We just actually solved for A, so we can plug everything in now. So A is 13.2 squared. C is 18.0 squared. And then B is 10.5 squared. And then we have to divide by 2AC. So 2 times 13.2 and then times 18.0, I guess. I don't know. The book puts 0.0 in. That seems pretty stupid. Anyways, if you do that, you'll get that B is approximately, cosine of B is approximately 0.0. Actually, they don't even give you a fraction in this. They just give you the decimal approximation. So 0.0816477 could give an exact number because it's a rational number, so it's finite decimals, but that's all right. Maybe it's really long. I don't know. So cosine B is approximately equal to that. So if you take cosine inverse, you get cosine inverse is approximately 0.816477, which is approximately 35.3 degrees. And you can go through a similar procedure to find angle C. So I think that's all. There's some parts here. There's like application, which is kind of dumb. The application's on navigation, but it's no different than what we're doing. So I'm not going to bother that. It's like a word problem, basically. And then there's area triangle. I don't think we'll need that. So that's all for today. This is 6.6 on law of cosines, and I will be assigning. So your exam is due, like I said, Wednesday, and I think we didn't have a quiz on the latest homework. So we'll have a quiz on Thursday, and then I'll assign a new homework on Thursday. And we might have this homework and then maybe one more or half a homework. I'm not sure. In which case maybe I'll just combine them both. So this is, you either have one homework or 1.5 homeworks. I'm not exactly sure. Don't quote me on this. But we're very close to the end. We might get done a little early, in which case we can take the final early, maybe, depending on everyone's schedule. And that's another thing we'll work out too. What's the best time to take a final? What works for everyone's schedule? Because I don't want everyone to have to take I don't want anyone to have to take like 3 finals at once. I had to do that last semester, I think, and it was god awful. I had like 3, because I'm a grad student, so I'm teaching, but I'm also taking my own classes. I teach this class, I take 3 classes, and I'm doing research. I'm working on my thesis on top of that. So I had to teach, and then I had 3 finals all happening at the same time, and it was awful. It was like the worst semester ever. Last semester it was awful. But anyways, enough of my ranting. We'll work out the final, so the fewest number of people have to take multiple finals at once. So let me end this video now. I've been going on long enough.